Hi, this is Mrs. LaBarbara. This is AP Physics, Mechanics C. This is a rotation review. Question number 3. A large circular disk of mass m and radius r is initially stationary on a horizontal icy surface. Person mass m/2 stands on the edge of the disk. Without slipping on the disk, the person throws a large stone of mass m/20 horizontally at the initial speed v0 from a height h above the ice in a radial direction, as shown in the figure above. The coefficient of friction between the disk and the ice is mu. All velocities are measured relative to the ground. The time it takes to throw the stone is negligible. Express all algebraic answers in terms of mr, v0, h, mu, and fundamental constant as appropriate. Question number 1. Derive an expression for the length of time it will take the stone to strike the ice. So basically find the time of the stone. So let's see, what do we know about a stone? We know the stone's mass, we know stone's initial velocity, and we know that velocity is horizontal velocity. Since the stone is in free fall when it's out of the person's hand, so there is no horizontal acceleration. The stone's initial vertical velocity is 0 because the stone was thrown horizontally initially. The stone's acceleration in the y direction is negative g. This negative means downward. Remember, g is never negative. We also know the displacement in the y direction is negative h. Again, this negative means downward. This is a kinematic equation because we know whenever we know 3 quantities in kinematics, we can figure out the rest of the quantities. Look at your reference table to see what equation is best used to find t. You will find this equation. Delta y equals v0 y plus 1/2 ayt squared. So because in this equation, the only unknown is t. So from here, substitute everything else, we have t equals to 2h over g. Next part, assuming that the disk is free to slide on ice, derive an expression for the speed of the disk and the person immediately after stone is thrown. So this is to find the velocity of the disk and the person. Let's see, you're probably wondering, is the stone sliding and rotating? As a matter of fact, the stone is only sliding, it's not rotating. This is because there is no torque acting on the disk or the person, because the force is directly passing the center of the stone, so there is no rotation of the disk. I mean, the force is passing the center of the disk, so there's no rotation of the disk. The disk is only sliding. The disk and the person is only sliding. So let's see what we know about the disk and the person and the stone. Let's see, the disk and the person, we know the total mass, we know coefficient of between the stone and the ice, we know stone's mass and stone's initial velocity. This is obviously a conservation of linear momentum question. So total momentum before equals to 0 because there is no net force on the whole system. The system consider of the stone, person, and the disk. There is no net force. All the force is internal, is between the stone and the person and the disk. So the total momentum, linear momentum before is 0, total linear momentum after has to be 0. Total linear momentum after is the stone's momentum plus the momentum of the disk and the person. Stone's momentum is its mass times its velocity. Disk's momentum is and the person's mass times that velocity. So from here you can figure out the velocity of the disk and the person is negative 1 over 30 times v0. This negative means the disk and the person is moving in the opposite direction as the stone. Now, derive an expression for the time it takes the disk to stop. Again, to find the time of the disk. So again, the person and the disk is a whole system together. So let's see what we know about person and the disk. So we know person, disk, we know their mass. We know coefficient is still mu between the disk and the ice. We know initial velocity from last question is of the person disk is 1/20 v0. We also know the final velocity is 0 because it comes to a stop. So what else do we know? Well, the disk is moving. We know the net force acting on the disk is friction. So that friction produced the negative acceleration. This negative basically means the disk is slowing down to a stop. So from here, we can figure out acceleration is negative mu g. So if we know the acceleration, we know initial speed and final speed, we can find the time using kinematic equations. So Vf equals Vi plus At. From here, we can find T equals V naught over 30 times mu g. Now the question has changed. So now the person stands on a similar disk of mass m and radius r that has a fixed pole right in here through the center, so that it can only rotate. It's not going to move linearly or translation. Doesn't have translation motion. So only have rotational motion. Now the person throws the same stone horizontally in a tangential direction at initial speed of V naught. As shown in the figure, the rotational inertia of the disk is mr squared over 2. You are asked to derive an expression for the angular speed omega of the disk immediately after the stone is thrown. Since the stone has no translational motion, and we know there is no net torque between the stone and the person disk. The only torque or net force is between them. So we know angular momentum has to be conserved. Angular momentum, let's take a look. What do we know? We know the disk has a radius r, so we know the disk's moment of inertia is 1/2 mr squared. We know the person, since the person is standing on the edge, so the person's r person, this one should be r person should be equals to r. So I of the person is mass of the person times the radius of the person, which is 1/2 mr squared. We know the stone's mass, we know the stone's velocity, we also know the stone has the distance from the center is r. So for a particle such as a stone, its angular momentum L equals mr squared times omega, I omega, right? Since omega equals V over R, so this expression can be written as mRV. M is the mass of the particle, R is the distance between the particle and the rotation axis, and V is the speed of the particle. So from here again, Ls equals 1/20 mR, because this R is the same as big R V naught. Angular momentum is conserved. Angular momentum before is 0. After is angular momentum of the stone plus angular momentum of the disk and person's system. We know this has to be opposite. That's why I have a negative here. So from here, after you plug everything in, you should have omega of the disk and the person should be V naught divided by 20 times R. Next one is next question. So it's similar to last one, except now the person is standing on the disk at rest, not at edge, but at r/2 from the center of the disk. So again, the person throws the stone with the same speed. The question is the angular speed of the disk and the person system immediately after throwing the stone from this new position greater than, less than, or equals to the angular speed found in the last part? So how do you compare the angular speed? When last part was on the edge, now it comes closer to the center. Is it going to be faster or slower? So how do you justify your answer? So from what we have before, angular momentum is still conserved because, again, the whole thing action is between the stone person and the disk. So if we treat the whole thing as a system, there is no external torque. Angular momentum is still conserved. So now, what is angular momentum of the stone? Angular momentum of the stone is, remember, mRV, but R has changed to 1/2 of R. The disk's moment of inertia is still the same. However, the person's moment of inertia has changed because the person has moved toward the center. So the distance between the person and the center is 1/2 R now. If we use this, substitute everything in, you will find the omega of the disk and the person is V naught over 25R. Remember what we had before? V naught over 20R. So now this is less. So the answer is less. That's it for today. Thanks for watching.